ultrastructure. And this is essentially the story of me trying to understand the notion of ultracategory, which was something I could not really understand. This talk is based on a preprint that you can find online. That's the title. This is where you can find it. And the plan for the talk is to give you a little bit of motivation. And the motivation is really going to be understanding ultra products, whatever they are. Whatever they are. And then we'll translate the question into a topos-theoretic question at the beginning, and then at the end of the talk we will go back to ultra products and see what we have learned from this translation process. Okay? That's the plan. First of the logic is special in many ways, and I say this sentence in a negative way, meaning, meaning that we do like our first order logic, but it doesn't behave as nicely as other logics, I would say. Let me make a very concrete example. If I take an essentially algebraic theory, so a category with finite limits or a finite limit sketches depending on your language, then its category of models is co-complete. So I can construct co-products of models and I can be happy. Like the category of models is very good behaving. And this is the story of locally presentable categories in a sense. And this allows for several construction, including free models. And people that study monads really understand why free models are cool in a sense. And yeah, as I mentioned, the category of models of a first order theory may not be complete and co-complete. And my favorite example when people ask me is the category of fields, which does not have products in general. And so studying first order theories is harder than studying essentially algebraic theories. And okay, for people into dualities, this is witnessed by the fact that the category of models has less properties in general. Okay. That said, though, there is something which makes it special in a positive way, and these are really ultra products. Ultra products are the fact that given a family of models, and there is a way to construct a new model, which morally is the product that we wanted to have and we don't. And although this way to construct it goes through the fact that we need to specify a ultrafilter. So you need to say, okay, I give you an additional data, this ultrafilter, then I can actually construct a model, and the notation in general is this one or something close to that one, which really shows the idea that it is a kind of product, but twisted along or quotiented along this ultrafilter that I have to specify. And of course, this construction is not allowed in any kind of logic, and so this is the positive sense in which first order logic is special. And the construction is functorial, which amounts to the fact that, which amounts to the fact that when I specify one ultrafilter, I get a functor from indexed set of models into the category of models. Okay? For those of you that don't know what an ultra product is, what an ultrafilter is, it really doesn't matter for this talk. I think this is a good feature of this talk. You can have this very categorical point of view on the story, which is that the construction of ultra products is the data of this family of functors, this family of operations over your category of models. Okay?
But whatever an ultrafilter is this construction functorial in the ultrafilter also?
We will talk about that. Okay, great. Is it okay? Okay, if you have a question, this is a good moment. Yes?
So, what does it mean for fields? Like, take characteristic 2, characteristic 3, take the product, and...
in that case, I think you get Q, I think. I mean, it depends. No, it actually does not depend on the ultrafilter you choose in that case.
I should think of this problem as being a set quotient.
Yeah, it's the big quotient. Yeah, it's a set quotient. Like you take the product of the structures and then you put on it a special equivalence relation. Yes.
Whatever.
I was wondering whether the attractions are imagined in the sense that if you take two attractions, so they give fields, equivalent.
No, they might give different objects.
Okay.
Absolutely, they might absolutely give different objects. So the ultrafilter does matter. Yes. And I also chose this notation with the integral. It would be too long to explain why. You can take it as a kind of fashion notation. I was hoping Jacob would. Okay. So ultra products are important. Why are they important? Because once you have the construction of ultra products, then you can deliver very nice proofs of compactness theorem for first order logic and also completeness theorem for first order logic. So they really, in a sense, characterize or are defining properties of first order logic. So understanding them is important. And actually, for those of you that are into universal algebra and Birkhoff-like theorems, you can get Birkhoff-like theorems by using ultra products. And so really, in a sense, they characterize first order logic. And this was what Makkai wanted to show in a sense. So we can get to the original motivation for this talk. As I mentioned, I wanted to understand ultrastructures. And ultrastructures were introduced by Makkai in order to axiomatize the operation I presented before, which is the existence of ultra product on a category of models. So he wanted to capture this construction, and this structure on the category of models is the main technology to prove the conceptual completeness, which is this theorem here, which says that if I have if I have a morphism of pretopoi such that it induces an equivalence of categories on the models, then actually it was an equivalence of pretopoi. So it is a kind of structure, syntax semantics result, but not entirely. Well, doesn't matter. The problem of ultrastructures is that they are a very complicated and technical notion. The person that, in my opinion, knows it the best is Zawodowski, I don't know how he's there, who uses them to prove a Lux descent result in his thesis. And it's a very heavy notion, and it's something that many people even thought maybe it's not exactly the right notion that we want. There could even be some small mistake in the axiomatization because it's very heavy, and I will not give it today. I wouldn't have the time to do it. And until 1995, besides Zawodowski's work, which I don't remember in what year it was, there were news on this notion. Like there was work using ultrastructures, but understanding ultrastructures, no news. And then in 1995, Marmolejo's PhD thesis, there was, I think, an important step in understanding what ultrastructures were, and he introduces the notion of wash category, which appears in my paper, a variation of which appears in my paper. So there was this step, and then no news again until 2019. I want to stress on the time gap between these events. No news again until Lurie's ultracategories. And the notion of Lurie is different from Makkai's. And the approach of Marmolejo is again a bit different from Makkai's. Of course, one can tell that there is inspiration and they are related, but these approaches are kind of different one to each other. And I couldn't accept it in a sense, and this is really why this talk exists and the paper exists. So the big question for me is who's right, which is the correct notion of ultracategory. And so my idea was, I honestly do not know. I will knock at the door of topos until the topos tells me. And so this is more or less what we are going to do. I want the structure of ultracategory to emerge naturally so that I can axiomatize it's exactly what I need and not over-axiomatize the notion. Okay, so little recap. In the case of essentially algebraic theories, I have any limit of models. And in the case of first order logic, I have ultra products and directed colimits of models. I did not mention it before, but it's well known that I have directed colimits of models. And in the case of geometric logic, I only have directed colimits of models. So This is something that topos theorists are very aware of, and if you aren't, just believe it. It's not hard to prove. And so when you look at this story in this way, I thought, can we use the fact that we have these constructions in order to really make emerge a property of the fragment of logic I'm studying? And what does even this question mean, in a sense? And so the answer is that we need an environment where all these theories live together in order to ask this question. If I want to characterize essentially algebraic theories among other theories, I have to say where I embed them, in a sense. And if I want to, first of the logic to emerge among something, I have to tell you where I do this story. And so, okay, the answer to the question is clearly the theory of classified topoi. I study the situation among topoi, and I want coherent topoi to be special among the others. So, but they are all classified by some topos, and so the idea is that if you have an essentially algebraic theory, then they correspond to topoi of this form. The classified topos is of this form. And then for first of the logic, I have coherent topoi, and for geometric theories, I have topoi in general. Okay. And for the category of points of the topos is exactly the models of the theory. Yes.
Doesn't coherent logic correspond to the positive fragment of first order logic? Where does you get the negative?
Of course, I have moralization going on. Yes, I mean, it's a good question, but let me go on, please. Moralization solves the problem. Let's put it this way. Okay. So, for example, in the case of an essentially algebraic theory T, the points of this guy is exactly the category of models. So, this slide essentially tells you how we take the problem and we move it to topos theory. So it's going to be a story about topoi and classified topoi. Okay, so what I want to prove is that coherent topoi, which correspond to first order logic, if you want, should be special among topoi. That's what I would like to claim. And the answer is going to be yes, but maybe we'll start from something simple, something that we can actually compute together. And I will start from recalling you that I can understand colimits via Kahn extensions. And in general, when I have a diagram D, and I want in a category C, and I want to understand whether this diagram has a colimit in C, this reduces to the fact that I can compute this left Kahn extension. And if I wanted a limit, was the right Kahn extension. Okay? This is clear. I will just assume it. And another way to say it is that when I look at the diagonal factor, which is just I mean it's just another way to write this. It has a right adjoint or a left adjoint, depending if I want the limit or the colimit. So in a recent paper with De Souza and Gabriele Lobbia, we introduced the notion of Kahn injectivity, which already existed in the Pusetta case. In order to study in a general two category exactly this kind of situation. So in this case, I would say that C is left or right Kahn injective with respect to this map, if I can always compute the map. Okay? And for example, the first proposition we will see is that the terminal geometric morphism can test completeness. So what does it mean, this sentence? That in complete analogy to the previous situation, where I was using this terminal map to test completeness or co-completeness, I can use the terminal geometric morphism, which is this one from set to the D, which is my walking diagram, if you want, into set to test whether I have limits of shape D in my topos. Okay? Notice that ultra products haven't entered the picture. We are solving the much easier problem of essentially algebraic theories for the moment. But it's going to be something from which we learn. So in this case, again, if I am time injective with respect to this gamma, and in this case I really want to say right time injective, then I can test completeness of what? Completeness of what though? Not of the topos, of course, but of its category of points, right? And I mean, this is the proof. It's in a sense, it's just you write the definition and you discover that that's what we have been saying the whole time. Because here, when you compute this, it's points of B to the D. This is just points of B, and this map is the diagonal. So to have a right adjoint means that I can compute the limit. Okay. And essentially, algebraic theories are injective. What does I mean? This should be true because the category of points has limits. So this has to be true. And this proposition appears, for example, in a paper by Johnston about factorization system. It's proposition 2.1, I think. So the classifying topos set to the C of an essential algebraic theory is weakly Kan-injective with respect to any morphism. And it is Kan-injective with respect to geometric embeddings. I didn't say the difference between weakly Kan-injective and Kan-injective, but it's more or less what you expect. This diagram can either commute up to ISO when I do the Kan extension, or maybe not. And that's the difference between the two. So this is what I'm saying. When I have a geometric morphism here and a geometric morphism here, I can always construct this geometric morphism if this is set to the C. And again, this is not my work, this is already in the future. And the proof of it is very nice. I think I like it. The idea is that here I take the unit embedding from C up into set to the C, and then I just go through this in the wrong way, which means that I have my set to the C. Here I take the F upper star into F, then I go down into G with X lower star. And when I say wrong way, I mean that once I do the left adjoints and once I do the right adjoint. So there is no reason why this should be my friend in this story. And then I just can extend this here. And this is going to be my H upper star. And why is it going to be co-continuous and lex? Well, because this guy is definitely lex, and this is the free completion under colimits, and then classical theory of category theory, the extension is co-continuous and lex. So it is the inverse image of a geometric morphism. And it is not easy, it's not trivial, but it is true that in this case, you can actually also compute H lower star, and it is the left hand extension of the right adjoints. But this is, I mean, this is true, but you shouldn't expect it, in a sense. It is something that when I proved it, I couldn't believe. It is kind of wrong that it is true. But it is very important in the story. Just keep it in mind. Another thing I want to say is that actually here we are computing a right hand extension in the category of topoi, and yet I do it via left hand extensions. There are many reasons for which this is true, but I will just stress on the fact that right hand extension in a general two category do not look like right hand extensions in cut in any sense. And in this case, it's evident, right? Okay. So we are convinced that I can use Kan-injectivity to also isolate classes of topoi with special properties when it comes to their category of models, right? How much time do I have?
About 6.
Oh, okay. It's going to be fine. Okay. So the next step is to show that coherent topoi are Kan-injective with respect to something, and then I want the ultrastructure to emerge from this fact. Okay? So a geometric morphism is flat when its direct image preserves finite coordinates. Okay, this is just a definition. You cannot bite. It's okay. And the theorem is that coherent topoi are Kan-injective with respect to flat embedding. And this is going to be my property, the property I like. I mean, remember, Lex theories were injective with respect to any embedding, so in this case, the flat ones. I should say, but I don't have much time, that the notion of flatness was introduced by Joyal for the case of locales, and it wasn't studied for the case of topoi. And that this theorem, I mean, it appears for the first time in my paper, but a version of this theorem for internal locales in a topos already appeared in a paper by Johnston that Gleason covered too, in a section which is kind of remote. And but I mean, one can derive the theorem from Johnston's one, but my proof is direct and it is more modular, so it works better for generalization. So this is the one I will comment on. So let's do it together, because it's actually not too hard. And also the idea is super nice in my view. So that's the situation. This is my coherent topos, and I want to extend. And I have no clue how to do it. But I can be lazy. I can be lazy and include my topos in its canonical presentation, the one where I choose coherent objects. So now that I'm lazy, I know, and this presentation, the right adjoints preserve directed coordinates. This is just true. Okay. So now that I'm lazy, I can find H, because I proved it before. I'm injected with respect to anything. And now I want to prove that actually this map lands in the image of J. Very, very general topology proof, in a sense. So how do you prove it? Well, this is the ISO we need to show, because if this is true, then automatically it factors through. And then you just write some time extensions, and it works. But the important part is here. Why is it? I mean, this is very formal. I'm not doing anything. The non-trivial part is why here J lower star should preserve this scan extension. This is very important. And it's non-trivial because it's a right adjoint against a left scan extension. So it's really trivial. And the reason is that when you open up the definition, because the morphism is flat, this diagram will be directed, and J lower star was preserving directed coordinates. So this is the key aspect of the story where I isolate where flatness is important. Flatness allows this diagram to be directed, and then I knew that J lower star preserved directed coordinates. So the nice part of this story is that it's very modular. If your right adjoint preserve shifted colimits, then you can tell what notion of flatness will generalize this. Give me a moment, it's going on. So because I lower star preserve finite colimits, the diagram here is filtered, and so J lower star preserves the diagram extension. Okay. So yes, coherent topoi are special, but this talk was about ultracategories, right? And I have like 2 minutes, so it should be easy at this point. So let's do it. So the first thing I tell you, and this observation is something I really, it appeals well written, mostly in the work of Marmolejo, but it was of course known by people like Isbell and Joyal and whatever. If I take X a set and B of X the space of ultrafilters, in the sense of R if you want, then the inclusion, this inclusion here, when I take shifts over it, it's flat. Aha, so finally there is a connection in the story between ultrafilters and something that I spoke about in this talk, right? So I have a flat embeddings here. So that means it's okay, in the specific case where the topology is discrete, shifts over X is set to the X. Okay. This is okay, this is important. So that means that if I look at this diagram here, this map is flat. Okay, this is the one I just described. And this is just a factorization of what's happening, where here I could put the discrete topology over B of X. Okay? So if I now consider a coherent topos, and I look at this diagram, I can extend, right? I have this extension because the map is flat. Now you write this diagram and you look at it very intensely. I have a map from points of E to the X to points of E to the beta of X, which just comes from the abstract nonsense of this diagram. I just rewrote it, and now I carry it, and I get this map. This is my evaluation against the ultrafilter. This is why it's so important that beta of X appears in the exponent, because I can carry around it. And so now in the rest of the paper, I axiomatize the properties that this thing has just by abstract nonsense, and I use them to give my definition of ultrastructure, which happens to be Lurie's one. I know. And so I cannot present it here, so you will read the paper tonight. But this is the end of this. Thank you.
Any questions? So, at some point you mentioned something that sounds false. But
Yes.
Yeah, can you go back to that slide? Because
no,
proof of that result is just a game of Kahn extensions. What sounds wrong about it?
I will tell you.
I know how you proved it. I did it during like slide 17. It's a very evident fact.
I lost it.
Yeah. No, it was.
I don't remember where.
No, it was after that. No. Wait. That. No.
Yes.
That
So I will tell you.
H lower star is evidently that kind of extension.
So what's the problem? Why you shouldn't believe it in a sense when you write it down? Because this is a right adjoint, right? And so you're taking a left Kahn extension of two right adjoints. There is absolutely no reason why this guy should present limits. Like, then you do some Kahn yoga blah blah, and it is true. But when you look at it and you just write a left Kahn extension preserving limits,
Nerves preserved.
yes, but it is a different situation. It is not.
I don't.
We will,
We can find later.
yes, exactly.
But thanks.
But I mean, anyway, it's true. So it's not.
Yes. No, I agree. It's,
Yeah.
You mentioned your methods were modular with respect to some of the colimits. I'm wondering if you have thought about what happens if you allow for certain kinds of infinitary disjunctions where they are bounded by some regular cardinal.
So like kappa topoi, where the reflector is flexed. I thought about it. I don't remember if I mentioned it in the paper. Maybe I chose not to do it. But yes, it's actually very easy to look at this proof in a modular way and say, okay, this is how the statement is going to be.
Can I ask for a sanity check on the last slide with
The last slide
with the formula of the product source?
here.
Yeah, up to that? Yes. So if x is finite,
Yes.
then beta of x is just x.
Yes.
So this is just for each element in x is just a projection, right? So there's nothing interesting going on from
Yeah. Well, and there should.
Okay. So I guess it answers my question of the fields before. So thanks.
one more question.
So what are the ultramorphisms in all of this? Right? I mean, the very notion of ultra factor and
Yes.
ultra factor, right?
This is so. If you look at the story, the way I tell it, the correct notion of ultramorphism is left ultrafactor, and like Lurie is correct in that. But the notion of ultramorphism does appear, and it's too long to say now, but you can really tell what's the difference and in what sense one notion, like what Makkai wanted to recover is the red topos inside the coherent topos, and instead what Lurie wanted to study is the topos around it. And so if you choose left ultramorphism, then you recover the topos when you do the duality.
I know Lurie also, right?
Okay.
But then question is how, from your analysis, this sort of you can derive that such a thing as an ultramorphism exists, and why Lurie and not Makkai?
I'm sorry, I have to redirect you to the paper. I discussed this in the paper, but it is a long story. It's not a 2-sentence.
Maybe we can continue the discussion afterwards. We can consider.